So, welcome to Crossroads. Thank you for joining us again, like every month, to think about what intelligence is and what parts of science can help us answer our questions about its mechanisms and mathematics. This is put on by Cross Labs, which is a research institute in Tokyo and Kyoto aimed at understanding the mind through computational research. We explore ideas about brain science, information sciences, artificial intelligence, and artificial life, and how they can enable new technology and changes in society. Of course, the cross and crossroads means we go interdisciplinary, and this is our monthly fun public forum on the sciences of mind and intelligence. We're supported by Cross Compass, which is a leading AI company in Japan working with technologies such as manufacturing, gaming, and other industries. Before we start, I wanted to give a special thanks to Olaf, Antoine, Stephen, and Arisen Katsu-san for their support as always. And this talk will have three parts. First, we'll have the talk by our guest speaker. We'll then have a Q&A on YouTube, and then we'll have an off-stream discussion. So today it is my pleasure to introduce our speaker, who is Stefanos Nikolaidis, who is an assistant professor at the University of Southern California, where he directs the Icarus Lab. And the topic today will be towards robust human-robot interaction, equality, diversity approach. Okay, Stefanos.
Thank you very much, Lisa, for the great introduction. And it's a real pleasure for me to be speaking about this work on robust human-robot interaction, quality diversity approach. And so, as Lisa said, I'm an assistant professor at the University of Southern California, where I direct the interactive and collaborative autonomous robotic systems, also known as CAROS lab. And our focus is on enabling robots to help people with everyday tasks. So, for example, we want robots to help people with disabilities on tasks like hair combing, meal preparation. And the focus of this group, of our group, is how we can make robots interact with users over long time scales and also interact with multiple users in the real world. And to be able to do that, what we need to do is we need to be able to identify and account for undesirable behaviors, for all the different things that can go wrong when you have a robot in a real world setting interacting with users. And there are different ways to achieve that, and one important aspect of that is to implement a system and test it through a user study. But in user studies, there is a limit on how many environments we can cover and how many user behaviors we can test. And therefore, our approach is how can we automatically generate scenarios in simulation to better understand and test complex human-robot interaction systems. And so as an example in this talk, I will take the shared autonomy algorithm, shared autonomy via hindsight optimization. And the way this algorithm works is there is a system, there is a robot, and the robot tries to help the user achieve a goal, for example, picking up an object. But the robot does not know the user's goal, and therefore the robot observes joystick inputs, observes inputs that the user provides through a joystick interface, and then infers a probability distribution over goals, and then assists the user for that goal. And so to give an example, here we have two goal objects, a black T and a white distractor object, and the user points the joystick to the left, so provides a low-dimensional input. The robot understands that the user wants to go to the black object because the user moves to the left and performs a constrained motion to pick up that object. And so the question, and this is a very, very robust system, so I've tested this system extensively myself. We have actually also given the system, and we had the people with spinal cord injury in the past work with the system and implement that system, and it worked very, very robustly. And so the question that I'm going to ask is, can we actually try to find undesirable behaviors? And can we do this through scenario generation? So can we generate scenarios in simulation that reveal system failures? Because if we can do that, that would be an important step towards deploying the system in a real-world setting over long time scales. Now, what is scenarios in a shared autonomy domain? Well, these are joystick inputs. So this is an input of a sequence of inputs that a human can provide to the system, and object location. So moving goal objects around. So we will vary these things and try to find scenarios and try to see whether we can actually break the system. Now, one approach is to formulate the scenario generation problem as a single objective optimization problem, where we try to find the global optimum. But this would result in a maximally adversarial scenario where the user points the joystick to the wrong direction, or the user is deceptive or tries to confuse the system. And these scenarios are easy to find, and they are pretty unlikely to occur in the real world. And so instead, we are interested in a diverse range of challenging scenarios. So we want to have a diverse range of high quality solutions. And so where we were thinking about being able to address this problem, we actually realized that there is an entire community or sub-community that focuses on finding a diverse range of high quality solutions. And that's a quality diversity problem. And so in single objective optimization, typically you try to find a global optimum. In multi-objective optimization, you have two or more possibly competing objectives and you search for a Pareto front. Diversity-driven search does not care about objectives. Instead, it has two or more measures and tries to find a solution for every output combination of a measure function. Quality diversity has one or more measure functions, and these are the metrics of diversity that we want to have. So we want to find solutions that cover the space specified by the measure functions. But there is also an objective that we want to maximize. So there is an equality F that we want every solution to have as high as possible, while having diversity with respect to the measure functions M. And so formally, we assume an objective F that we want to maximize, and some measures M, these are the measures of diversity, these are measures of interest that we want to have diversity for, and these form a measure space. And our objective is for every output combination of the measure functions, find a solution so that the quality of the solution is as high as possible. Now, an issue with that is that the measure space is continuous and we would need infinite memory to cover that space. And so instead, what many quality diversity algorithms do is they try to optimize and approximate quality diversity objective, where we tessellate the space S into M cells. So we discretize that space. And then we search for a collection of solutions so that each solution theta I occupies a unique cell. And also the quality of all the solutions is as high as possible. So basically, we try to fill in the cells of that space with as many solutions as possible, but also solutions of as high quality as possible. A state-of-the-art quality diversity algorithm is MapElite, where it maps a high-dimensional search space to a lower-dimensional measure space. So it tries to, remember we have this partitioned measure space, and it tries to fill in that space with solutions, but also tries to maximize the quality of the solutions in that space. And the way MapElite works is that it retains an archive with the best solutions found. So it keeps track of the best performers. And then once it finds a better solution for a given cell, it replaces a previous solution with a better solution and does this iteratively. And so specifically, MapElite starts by sampling initial solutions from some fixed distribution, and these solutions populate the archive. And then MapElite selects uniformly solutions from the archive and perturbs them with some isotropic Gaussian noise. And it does this iteratively. And the key insight is that existing solutions act as stepping stones. So a high-performing solution in some part of the archive is likely to perform well also in some other part of the archive later on. And that's a key idea on how MapElite uses existing high-performing solutions. And so what we asked is, can we generate scenarios in shared autonomy that result in system failures? Now, the measures of diversity that we have are distance between objects, so how far away objects are, and also human variation, which is how noisy the human user is. Intuitively, if objects are very, very close to each other, then the system may get confused. And also, if the user is very, very noisy, also the system will have worse performance. And so we want to find a diverse range of scenarios where objects are close to each other, but also objects are far away from each other. And also scenarios where the user is optimal, but also scenarios where the user is noisy. And see whether in any of these, or in a range of these cases, can we actually find failure cases where we break the system. And if we do that, we get an archive of scenarios. So the x-axis is variation, is how noisy the user is, the total amount of noise. The y-axis is distance between objects. So larger values mean objects are further away from each other. And each cell here represents a scenario. And the color of the cell represents the quality of the solution, where solutions of higher quality mean worse systems performance of the shared autonomy system. Because remember, we try to find scenarios that break the system. So a high quality scenario is a scenario where the system failed. And so the scenarios that are in red color are scenarios where the robot was unable to find the true user's goal within a time limit of 10 seconds. And so the first thing that we noticed is that MapElite performed significantly better than uniformly sampling scenarios, uniformly sampling scenario parameters. We call this random search. And also better than CMAS, which is a state-of-the-art derivative-free optimizer that tries to find for a single global optimum. But I think what is very, very interesting is to see what these failure scenarios that MapElites found look like. And so this is a success case, right? So this is a success case where the user points to the left object and the system successfully understands the user's goal and moves towards that object. Let's try to see some failure cases that the system found. An example failure case that we have here is when we have a scenario that there is a large variation. So there is a large amount of noise in human inputs. So we see this scenario selected here. And if we reproduce this scenario in the real world, what we have is we have a user. While the user's goal is the black object, the user points the joystick to the right, the white distractor object. That's because of the noise in user inputs. And this confuses the system. And so the system erroneously thinks that the user wants to go to the white object instead of the black object. And that's pretty much expected. If we have noise in user inputs and the system uses the joystick inputs as observations to infer the user's goal, then it will get confused. But I think what was really, really exciting is that we found failure cases even for an optimal human user. So even the total amount of noise is very, very small, we can still find some failure cases. And if we reproduce them in the real world, we see that the white distractor object was actually in front of the black T, which is the human goal. And even though the user optimally points towards the goal object, the system uses a distance-based observation function and gets confused and thinks that the user wants to go to the white distractor object instead. So this is an edge case that was completely undiscovered when we manually designed the system and tested the system, because when we were testing the system, we were just putting objects side by side, having knowledge of how the system works. And it's something that we missed, but it was automatically discovered with the MapElites. And so this shows that quality diversity algorithm MapElites outperforms random search as well as single objective optimization methods in scenario generation for human-robot interaction. And so we wrote a paper about this, and then we sent the paper to RSS, robotics conference, and it got accepted, and we were very happy about it. But reviewers pointed out two legitimate limitations. And one is that MapElites still requires a large number of evaluations to achieve good results, because MapElites is designed not to have any bias and to run for a very long time. And the other is that the generated scenarios are pretty simple, so we are just moving objects around. And so in the next part of the talk, I will talk about how we address each of the two limitations. And so for the first part, can we make the search more efficient? The way MapElites works is that we sample initial solutions from a fixed distribution, and then we uniformly select solutions from the archive, and we perturb them with some isotropic noise. Well, this makes the assumption that any direction is equally promising when we perturb the solution. That's the assumption behind an isotropic Gaussian noise. But can we instead generate solutions in a direction of maximizing the quality diversity objective, where the quality diversity objective is to find a collection of solutions that occupy as many cells as possible and are also as high quality as possible? So we try to fill in this archive of solutions with solutions of very high quality. And so what we would like to do instead of a random perturbation would be to try to compute some sort of a gradient of the quality diversity objective with respect to the current archive. Now, what does a gradient is? Gradient intuitively is a small change that is in the direction of steepest ascent. And so we would like to find some minimum change of the archive that results in a maximum improvement. Now, how can we change the archive? We can either add a new solution to an empty cell, or we can replace an existing solution with a new, possibly better solution at an occupied cell. And so the key insight is that we formulate searching for a solution that maximizes archive improvement as an optimization problem. And we use CMAS, covariance matrix adaptation evolution strategy, as an optimizer. And the way CMAS works is that it samples different solutions from a multivariate Gaussian, and then selects and ranks the best solutions based on some objective. But now we will select and rank these solutions based on how much they improve the current archive. And so this enables us to move in a direction of maximum improvement. And CMAS has also some very nice step size adaptation properties. And therefore, our insight was to combine MapElites, combine the archiving properties of MapElites, with the selection and ranking properties of CMAs, and we proposed covariance matrix adaptation map elites, CMA-MEGA, and we were able to show that this significantly improves the search efficiency, especially in continuous spaces. So this discussed the first limitation. Can we also make the scenarios a little more complex? Can we generate more complex scenes? And one idea to generate complex scenes would be to add more objects to the scene. But that is not exactly what we want, because we are not just interested in complexity, but we are also interested in scenes that are complex and also realistic. And so, for example, if we are in a kitchen environment, we would like the fruit to be on top of the table and the pot to be on top of the stove, but not like the fruit on top of the pot, for example, right? So there are specific realistic aspects of realism that we want to capture when we generate complex scenes. And therefore, the key insight was to illuminate the latent space of generative models, which means to train generative models with human-authored examples, and then search the latent space of these models with quality diversity algorithms. And especially with the CMA-MEGA, which the latest algorithm that I just discussed, which is very, very effective in searching continuous spaces. And we use this benchmark domain, the Overcooked game domain. So in this game, there are two agents that coordinate, and there is a green agent, which is a simulated robot and runs a partially observable Markov decision process in real time, or some approximation, a QMDB approximation of that, and tries to estimate what is a human subtask and then assist the human for that subtask. And there is also simulated human, which is a blue agent, and it runs based on some heuristics. So for example, if there is an onion, pick it up and put it on the pot. And the two agents need to coordinate to complete the task as soon as possible. And therefore, in this case, what we will try to do is we'll try to use latent space illumination, try to use quality diversity to generate environments that result in as diverse agent coordination behaviors as possible. Even though we are going to freeze the agent algorithms, so we are not going to change the agent algorithms, can we generate environments that result in very, very different behaviors? And the way to do that is we will use CMA-MEGA and search the latent space of a GAN trained with human-authored examples. And that will generate layouts that match the style of human-authored examples. And therefore, they are realistic in that they match the style. But at the same time, these layouts may not be valid because of different artifacts. So you see here that the generated layout has two human agents. It doesn't have a pod. Some parts are not easily accessible. And therefore, what we will do to make these layouts valid is we will repair them so that we find the nearest possible layout that is as close as possible to the input layout that is generated by the GAN, but is also playable. And we do this by formulating this repair as a mixed integer program, where the idea is that we want to minimize to find the minimum cost network flow. So minimize the number of edits that we need to apply to the input layout while respecting some playability constraints. So we formulate this as a minimum cost network flow problem. And then we will simulate the agents and evaluate the coordination behaviors. So coordination metrics are amount of concurrent motion, how much the two agents move at the same time, also whether the two agents get stuck, how much time they spend getting stuck, and so on. And then we update the archive. And we do this iteratively. And if we do that, so these are two example environments. So the left environment, you see that the two agents can coordinate very, very well. So you see that all objects are very easily accessible, and the agents can do the task very, very efficiently. On the environment on the right, you see that the two agents are going to get stuck here in the crossing. And then one agent needs to wait for the other agent to go pick up, because the other agent needs to go to pick up the dish. And so it's an example of much worse coordination, even though the two agents run exactly the same algorithms. And this environment is also pretty intuitive. So it has long corridors, right? The objects are not very easily accessible, but it was completely automatically generated. We can also use the same pipeline to find failure cases. So here you see the green agent, which runs a PAMDP and tries to estimate what the human subtask is. But when the two agents get stuck, the blue agent will start taking some random actions based on its heuristic. And therefore, what happens with the green agent, which has a belief on human subtasks, is that the belief, the probability distribution over human subtasks, will game domain to generate video game levels. And in fact, when I was, before coming to the States, I actually lived in Japan for 4 years, and I worked at a video game company in procedural content generation. And one of the things that I really quickly found out was that we spent a lot of time optimizing content, but then video game designers never used the content that we created, but it was a starting point for exploration. And so what game designers often want is they want a collection of diverse content. And therefore, what we did is we used some human-authored examples, human-authored environments to train a GAN. And then based on that, we generated a new environment. And also we had an AI agent simulate a playthrough in that environment. But instead of just sampling from the training distribution of the GAN, what we did is we used the CMA-MEGA to search the latent space of the generative model to have environments, to have game levels that are diverse with respect to number of enemies and number of sky tiles. And so this is a resulting archive of solutions that are, the red color solutions are all playable by the AI agent, but are also diverse with respect to the two measures, number of enemies and number of sky tiles. And so this is an example of a video game level that has a large number of enemies and a small number of sky tiles. This is an example video game level that has a large number of enemies and only ground tiles. This is the opposite. So this has a large, almost no enemies and a large number of sky tiles. And this is somewhere in between. And this is somewhere in between. And all these levels were automatically generated from a single run of CMA-MEGA. And so we see how integrated quality diversity algorithms with generative models can improve the complexity of the generated scenarios. Now, we wanted to come back also to the first limitation that says that map elites still requires a large number of evaluations. And all the algorithms that we have discussed, including CMA-MEGA, treat the objective and measures as black boxes. So they do not make any assumptions about any gradient information. But there are many applications where both the objective and measures can actually be differentiable. And so we define this a differentiable quality diversity problem. And an example application of that is the style gun and clip pipeline, where you have a latent vector and you pass it to a style gun and that will generate an image. And then you have a text prompt that says Elon Musk with short hair, for example. And then you pass both the image and the text prompt to a clip, which is a model trained by OpenAI, and that will give you a similarity score. And then the whole pipeline is end-to-end differentiable. So what you can do is you can do gradient ascent on the entire pipeline to maximize similarity. So that you find images that look like Elon Musk as much as possible. But what if we want to find diverse images? For example, images that are different, that look like Elon, but faces that look like Elon, but also are diverse with respect to eye or hair color. One way to do that would be to have a prompt that says, for example, a man with blue eyes, and then compute the similarity of an image generated by StyleGAN with a prompt, and then pass this as input to the clip model, and that would give you a similarity score. But then instead of trying to maximize or minimize that, we would search for images that across a range of different similarity scores. So we would search for images where the eye color is blue, but also images where the eye color is different than blue. And that would be a measure of diversity. Now, what is important is that now the pipeline here is also end-to-end differentiable. And so we could actually compute the gradient of both the objectives and measures. How to integrate objective and measure gradients in quality diversity search has been an open problem for several years. And we actually proposed the first solution to this problem. And this is a work that we presented as an oral presentation at NeurIPS this year. And in the next slides, I'll show you the insights, the key insights behind solving this problem. And so the differentiable quality diversity problem, we have map elites, which is, typically in map elites, what we have is we have a solution and then we apply some random perturbation of that solution to generate a new solution. But for the differentiable quality diversity problem, can we leverage gradient information to improve the search? Now, if we have one objective in single objective optimization and we have the gradient, then we can just move in one direction, in the direction of gradient ascent and improve the objective. But in quality diversity, we have an objective that we want to maximize and also measures, and we want to somehow cover the measure space. How can we use gradient information to cover the measure space? Well, if we assume two measures, M1 and M2, and we have a solution theta, the gradient of M1 with respect to theta is the direction of steepest ascent. The gradient of M2 with respect to theta is the direction also of steepest ascent of M2. And the negative gradients are directions of steepest descent. And therefore, we see that all these gradients form a coordinate system. And if we have some scalar values that we multiply the gradients with, we can perform some motion in this measure space, in this space formed by the gradients. And therefore, well, if we have one objective, then we move in one direction, and that's a gradient ascent direction. Now, if we have the objective and measures, well, because we want to cover the measure space, this implies some branching tree structure. But there is some directionality there in that we still want to cover the measure space while maximizing the objective F. And so we borrow the term arborescence from graph theory, where we want to show that it's a directed tree search, where we branch through with the measure gradients to cover the measure space, but we also have the objective gradient and therefore we also need to account for that and maximize the objective. And so in map-ellipse, we would apply some isotropic Gaussian noise, but instead, when we have gradient information, what we propose in map-ellipse via gradient arborescence, we can define a function that is a function in linear combination of the objective F and the measures. And then we can take the gradient of that function and perform gradient ascent with respect to that function. And that will maximize the objective and also perform some motion in measure space. Now, the next question is, how do we choose these coefficients that define both the direction of how we move in measure space, but also how fast we move with respect to the objective and measures? And one approach would be to sample the coefficients from multivariate Gaussian. But instead, what we will do is we will use exactly the same insight that we used in CMA-MEGA, where we will try to search for the coefficients that maximize improvement of the archive. And again, we use the CMA-MEGA to generate and sample coefficients and select and rank the best coefficients. A difference between CMA-MEGA and the new approach here is that in CMA-MEGA, we generated solutions and tried to find the solution that maximizes archive improvement. Here we generate coefficients and we perform gradient ascent steps for each sampled coefficient. And then we select and rank the coefficients that maximize archive improvement. So we search for directions based on in objective and measure space. And this is the result is a covariance matrix adaptation map-ellipse via gradient arborescence algorithm. And the way the algorithm works is that we have a multivariate Gaussian, and we sample coefficients from this Gaussian. And then we branch from each sample coefficient, we perform one step of gradient ascent in objective measure space. And then we evaluate the result of this gradient ascent step, and we update the archive with the resulting solutions. And then we select and rank the resulting solutions based on how much they improve archive, and pick the best direction that maximizes archive improvement. And at the same time, we use the same evaluation with the same selection and ranking to adapt the multivariate Gaussian with the CMA-MEGA rules, so that in the next iteration, we will sample coefficients that are more likely to result in improvement of the archive. And we do this iteratively. And so to provide some intuition of that, imagine that you are your parameter space is three-dimensional. And let's say that you are in a room and you sample some solutions in that room. And let's say that you have one objective and one measure. And so the objective and measure gradients form a two-dimensional plane. And so imagine that, therefore, the objective and measure space is a sheet in that room formed by the objective and measure gradients. And now what you can do is within that sheet locally, you search for the direction that will maximize improvement. And then you take one step in that direction. And then you recompute the objective and measure gradients. And so now the sheet has shifted a little bit. It has moved a little bit. And so the optimization landscape changes a little bit, but we assume it changes slowly. And we do this iteratively. And we actually were able to show that CMA-MEGA covariance metric adaptation map-ellipse via gradient arborescence was able to significantly improve the search efficiency in quality diversity search. And to come back to our original motivating application, we generated images that look like Elon Musk, but vary with respect to different characteristics. And so if we take some of the generated solutions from the archive of solutions, we see that we have images that look like Elon Musk, but as we go top to bottom, the hair color becomes more and more red. As we go right to left, the eye color becomes more and more blue. And these are two cherry-picked examples. And also we can do the same for Beyonce. So as we go from top to bottom, she becomes younger. As we go from right to left, her hair becomes longer. And this is also an example generated image. All the algorithms that I have discussed are actually available in PyRips, our open source library, and we have also implemented several tutorials, including finding diverse landing strategies for a lunar lander. So if you want to be able to train a lunar lander to land like a space shuttle, I definitely recommend that you check it out. This is the most important slide. So these are the students that have done the work, and specifically the work that I presented in this talk. It was done by Matthew Fontaine, who worked on quality diversity optimization and scenario generation for human-robot interaction. Sophie Su, Yulun Zhang, and Brian Chanaka have worked on environment generation that results in diverse coordination behaviors. And also Brian Chanaka has been leading the development of PyRips of the open source library. And so the main takeaways that I would like you to have from this talk is that there is a wide range of applications where we want to find a diverse range of high quality solutions. And one such application is scenario generation for human-robot interaction. And we have discussed how quality diversity algorithms can help search the parameter space, continuous parameter space, the continuous space of scenarios very, very efficiently, but also how integrating the quality diversity algorithms with generative models trained with human-authored examples can result in content that is diverse, complex, but also realistic. And with that, I would be happy to take any questions.
All right, great. Thank you so much for your talk. I'll ask a couple of questions and then we'll take some questions from the audience. And I did want to apologize to those people in the audience that noticed there was an internet issue during the middle of the talk. So the talk did cut out for maybe 5 minutes or so, 2 minutes, I don't know. If you have any questions, I think the talk was still understandable, but please feel free to ask questions in Slido if you have any, and be happy to go over some of those slides again. That's no problem. So one question I have is, what makes robotics in particular an interesting domain as opposed to, like, I don't know, games or maze navigation or some of these other things that we use quality diversity algorithms for?
Right. This is actually a great question, and it's something that we have been thinking a lot as we try to test things in games and try to apply things in more complex domains. And one aspect is that in robotics, there are less things that we can control. So in games, in a sense, when you control the agent and you test the agent, but you also have aspects of the environment that you can control. You can control some parts of the physics. In robotics, a large part of that is uncertainty. So there is uncertainty in the world. There is uncertainty in dynamics. There is uncertainty in the mass, the physical properties of the robot. And I think one great application of quality diversity is it enables us to account for this uncertainty. And so, for example, in some of the recent work that we just submitted we just put on archive, where we use quality diversity and differentiable quality diversity to find different walking gaits. This could be very helpful because the robot may not have exact information about the environment, may not know exactly if it's on a steep road or on a hilly road or on a grass, right? But what it can do is it can have this repertoire of diverse robot policies, and then it can perform online adaptation. And this was also like something that was done in the original MapElipse paper, where they had these hexapod robots, and then they were able to do damage adaptation. And so I think what quality diversity can help a lot is enable the robot to have some type of a repertoire of different behaviors offline and be able to pick these behaviors in real time when interacting with the uncertain and often unforgiving real world. And the other aspect that I would like to talk about is also in scenario generation. So we can generate scenarios in simulation, but I think what is very, very interesting is to see how much these scenarios translate to the real world when we have actual human users and actual robots interacting with each other. And I think that's a very challenging and interesting problem.
Cool. One more question I have before we head over to Slido for some audience questions. I guess related to what you just said, do you run into problems with the crossing the reality gap at all with like things that you see in simulation and then taking that and moving over to like actual robots?
Yeah, absolutely. I think it's clear that the simulation, the simulated agents are definitely more constrained than real human users when they interact with a robot and with the system. And some thoughts that we have on that is that, well, first, there is an increasing work in the robotics and human robot interaction community to build more and more higher and higher fidelity simulations. So, for example, like there is work in Georgia Tech that they built the assistive gym that has very, very high fidelity human models. And I think like work in that direction can definitely help bridging the gap. What I think is very important and was a little bit surprising to us as well is that you do not need very accurate models to find interesting scenarios. And so in Overcooked, for example, in the Overcooked game, we had a very, very rough human model that was based on some very simple heuristics, like an if then else statements. It's by any stretch of the imagination, it is not close to what you would expect when you have actual human users. It wouldn't match the behavior of actual human users. However, what we found is that when the scenarios that we generated for this agent interacting with a robot agent were actually perceived hard and challenging and resulted in poor coordination also when we had actual human users. So I think what is important to understand is that even though we don't have very, very high fidelity or very accurate models, we can still generate very interesting scenarios that translate to real world behaviors.
Cool. Okay, so let's head over to Slido and take some audience questions. Oh, we have a lot of questions, which is exciting. Okay, so we will take the first one. So someone said, Anonymous said, I am interested in starting to learn and play with the optimization of robotic actuators. Are there any specific physics simulators that you would recommend?
So right, so that's a great point. So I think the first, so I think it depends where you're starting from, like what the starting point is. I think the first step that I would suggest is you can use MATLAB. That's what I used in the past and designed some simple 2D planar manipulators, and then write down and implement some physics models. So I remember when I was in college, my diploma thesis was on Acrobot, which is a two-link planar robot that is only actuated in the middle. And then the idea is so it's a two-link robot, and then you have to rotate the second link and to use the momentum to bring the first link and also the second link balance on top, right? It's a nonlinear control problem. And this is something that you can test and implement and try it very, very quickly. So I would start on that, and then before moving to more like to more higher fidelity 3D simulators. And I think that would give a very good understanding of like the dynamics and physics and kinematics of robotics.
Okay, awesome. I think this next question was sort of answered during your talk, but somebody asked if it was possible, if plugged in with something like ClipDraw, if you could have a hybrid artist. So I don't know, are there any other artistic applications you might see of the work besides the image generation that you talked about?
Oh yeah, definitely. I mean, one of the things that one of my students, Matthew Fontaine, and others we have been working on is generating like having something like ClipDraw and generating diverse art. And I think that's something that we have touched upon a little bit, and we were actually be able to see a very diverse range of images. I think what is the benefit with latent space illumination is that it's not tied up to a specific generative model, but we can actually leverage any advances that happen in this space and search with our differentiable quality diversity algorithms the latent space and try to generate different types of content. And so I'm very excited about the future applications, not just in scenario generation, but also in computational creativity.
Well, we'll look forward to that coming out. Do you see any applications for industry that are particularly interesting?
I think there is a number of applications, especially in robust human-robot interaction, because one aspect before deploying robots in the real world is how safe they are, and have we actually accounted for all these undesirable behaviors? And so one application is in the manufacturing domain. You have robots interacting together with people and collaborate, like in assembly tasks. You want to be able to have accounting in advance in some sort of simulation environment for different things that can go wrong and occur, and take countermeasures for those. And another very obvious application is autonomous cars, autonomous driving. And I think this is a very safety critical application, that it's really important to account for these edge cases. We also have a project with the University of Kentucky and also a mining company there, where the idea is that we want to make mining safer, in that we want to have a robot manipulator collaborate with a roof bolter and also a miner in performing some operation called roof reinforcement, where basically they drill steels on the ceiling and then they put steel bolts, and that helps the ceiling not collapse. But it's a very dangerous operation, and it's also a very safety critical operation, in that the mining machines that are all running on hydraulics, so they are not like going to stop if something goes wrong. And so when it comes to a human robot interaction in the mining domain, that's also an application that we are very much looking at, how we can generate scenarios and make these algorithms run more robustly over time. Yeah.
Okay, great, thank you. So let's go back over to Slido and take some more audience questions. So another anonymous question: when generating new scenarios with the GAN, how do you make those scenarios solvable? Like, how do you guarantee that?
Yeah, so the idea is the following. So oftentimes you generate environments from the GAN and they may not be solvable, right? But and so what we do is, well, for the specific layouts that we have generated, there are two ways to do it. One is specify solvability as quality of the scenario, and then as part of the quality diversity problem, you try to find scenarios that are as high quality as possible, and so you search for solvable scenarios. The problem with that is that often you spend a lot of time generating layouts and environments that are not solvable. And so what we did in the Overcooked domain was we generated environments that might not have been solvable, but then we applied a mixed integer program to repair them. And the way we do that is we have as objective to minimize the number of edits that we apply to the input environment. And we also have some playability constraints. And this could be as simple constraints as, you need to have at least one human and one robot player, and at least a pot, and at least this number of objects. But there are also more complex constraints that have to do with reachability. So these are constraints that have to do that all objects need to be reachable, all important parts need to be accessible. And actually, we can the contemporary mixed integer program solvers can solve this type of programs very quickly, and therefore we can get levels that match the style. So they look very nearly identical to what the GAN has generated, but at the same time they are solvable.
Okay, cool. Thank you. The next question is from Ava, who says, I read your paper approximating gradients for differentiable quality, diversity, and reinforcement learning in arXiv, and found that CMA-MEGA performs worse than MapElite's in QD-GYM. Found that I think that the phenomenon is due to the different definition of gradients. So here's the question: what are the tasks that are suitable for DQD to solve, and what are their characteristics?
Yeah. So first, I think if we read the paper, we have different baselines, and the differentiable quality diversity with reinforcement learning, that was a paper written by Brian Chanaka and Matthew Fontaine, also in collaboration with Julian Togelius. So this is to give a little more context on the paper that the question addresses, it does perform better than MapElite's in most tasks. It performs comparably with a state-of-the-art algorithm named policy gradient assisted MapElite, PGAME, although slightly more efficient. So it has comparable performance, but in two of the tasks it takes longer. So the idea behind applying DQD to reinforcement learning, which is also something that is an important domain because that's also a domain where we want to have diverse policies, is that instead of having exact gradients, which we have in the style gun and clip pipeline, we try to estimate the gradients. And we estimate the gradients, we can estimate the objective gradients using stuff, the actor critic methods like TD3, but we also need to estimate the measure gradients, and for that we use the evolution strategy. So we use the OpenAIS estimator. And so I think there are several conclusions that we can draw from these experiments. And one is that first, it's important, if we have exact gradients, then the performance of DQT is significantly better, or at least was significantly better than any baseline we tested, for example, in the style gun and clip pipeline. However, if we want to estimate gradients, then the accuracy of the gradient estimation plays a role in performance. The second insight that we got from the experiments is that because the DQT algorithms that we have developed so far prioritize exploration. So the way covariance matrix adaptation map elites via gradient arborescence, so CMA-MEGA, the DQT algorithm that we propose works, is that it ranks on top solutions that discover unexplored parts of the archive. And therefore, it works significantly well in domains where exploration is hard. In the domains that we have tested so far, in reinforcement learning domains, exploration was easy. The archive was filled almost instantly, and optimization was hard. So in finding like very, very high quality solutions were hard. And this also was something that we think that right now the DQT algorithms that we have that have room for improvement. So overall, if you have a domain where exploration, like finding diverse policies, is very, very hard, then DQT algorithms is a great method to apply. And also at the same time, we need to account for how accurately we can estimate the gradients, because remember that in DQT what we do is we assume that we have gradient information, and therefore in that paper we only were able to estimate that using TD3 and OpenAIS methods.
Okay, cool. And our last point is kind of a comment rather than a question, which is fine. Another anonymous commenter said that computational creativity, robotics, I'm dying for seeing a robot creating stop motion by itself. Imagine the robot moving a puppet frame by frame. So that would be, I think, another interesting application. So cool. I don't see any more questions on Slido. There's a thank you from Ava, which is very nice. So I think now we'll go ahead and head over to our Zoom chat. So everybody can go ahead and grab the Zoom link out of the YouTube chat. We have it posted there for if there are any questions that anybody didn't want to ask, or you just want to come hang out with us. We'll be around for the next maybe half hour or so. So please join us. And thank you once again.
Thank you for having me.